All right, so what does it mean for a variable to occur free in a lambda calculus expression? The things you all just wrote down. That's what I'm asking you to tell me. Just read one. When a variable occurs free, it exists or occurs in the lambda function, but is free to be defined?
Yeah. I don't know how to put it into words. I could write it down like an actual function and say.
All right, so when we look at the body of a lambda calculus expression, right? So lambda calculus expression is the word lambda, followed by a parameter list, followed by the body, right? When we look at the body of that, as long as the production is the production that is the list containing two lambda expressions, where the lambda expression is just an identifier. So when the production of a lambda calculus expression that is an identifier, that variable occurs there, but is not bound by the parameter list of its of a corresponding lambda calculus expression. Make sense? Not defined there. So we might have a variable a defined and a variable x being used. So lambda, open parenthesis a, with an x over there, x would occur free because it's not bound by the parameter list.
So it's like if it says like lambda x and a, and then you use x after that.
Like this. X occurs free here. Because the only variable that's bound, or I'm sorry, a occurs free here because the only variable that's bound is x.
So then you're a correct answer would be anything.
Here, we'll let you try to answer it real quick. What does it mean for a variable to occur free in a lambda calculus expression?
Had its own line?
What?
Okay, can you repeat the question one more time?
What does it mean for a variable to occur free in a lambda calculus expression? What is a lambda calculus expression?
Speak that language on me.
Did you do your homework today? Yeah. Did you do it?
Yeah.
Are you lying? All right. So let's finish answering the last question from last class. I was kind of rushing right there at the end of class, so let's just start that one over. Then we'll look at today's homework, and then we'll talk about the next homework assignment. Right? How did today's go? Better than the previous one, even though it was harder?
21 was annoying.
Okay. I don't know what 21 was, so we'll look at it. Oh, okay. So, define. So we're supposed to do count occurrences, right? And count occurrences takes... Shut up! Count occurrences takes a symbol we're looking for along with an S list, where an S list is a collection. It's a list of symbols or S lists, right? So anytime we see an S list, we want to call count occurrences on that. Whenever we see a symbol, we want to check to see if it matches the symbol we're looking for. Okay? So, what I started writing last time, we'll just start it again, is I want to write a function called count. And count is going to take in a symbol along with an S list that we are looking for. Actually, let's just call it count occurrences. Good enough. Define count how do you spell it? Occurrences. 3 R's? 5 R's?
Yeah, that's good. The silent Q.
Yeah, this is the silent Q. Count occurrences to be a lambda that takes in a symbol and an S list. All right. And we want this guy to return the number of times S occurs inside of the S list. Right? All right. So we're going to keep going as long as there is a car to the S list. All right, so we're going to ask the question if, so again, remember last time, kind of our theme from last class as we were going through the homework assignment, is that all of these problems kind of have a similar structure to them. And I think there was one problem last time where Haxton had kind of a good solution, but it deviated from our structure, so I kind of showed you the worse solution to it, just to kind of stick with this drill of following almost a paint-by-number structure for different questions. So we're going to have our normal structure where we're testing whether a list has something in it. So if null S list, which means there's nothing in that list, which means there's not a car to that list, we're going to return something. Now, typically our pattern up to this point has been to do what? Return an empty list. Because what we're actually doing is we are finishing off a big recursive call to cons, correct? But in this case, we're doing some counting. We're doing some math. So if I have nothing to check, what should count occurrences return? If I'm trying to find out how many times a B occurs in the empty list, what's the answer? 0. So I'm going to boil down to 0 there. All right. So if what I'm looking at, it doesn't have anything left in it, we're going to boil down to a 0 because it's probably going to be the follow-through of a recursive call to the addition function, the plus sign, right? So when I'm doing the final unraveling the recursion of a cons, I need to have an empty list. When I'm doing something that's doing the unraveling of the recursion for a math problem, I probably need to do a number, okay? So in this case, what does count occurrences return for looking for S inside of S list? It returns a 0 if S list is empty. All right. Otherwise, we need to look at the car of S list. We know that the car of S list is one of two things. It's either going to be a symbol or it's going to be a list, right? If it's a symbol, we want to know if it matches S. So we're going to ask a question. So if symbol car S list, if that's a true statement, then what are we going to do? Well, we're going to ask the question. We want to know, does that symbol match S? So then if car of S list, so that's that symbol, if this guy, can we use the equal sign?
Starting route to Orthopedic Associates of Milwaukee.
Sorry, I need to make directions.
Guess it could have been way worse. Starting route to some gentleman's club or something.
That's after my appointment.
Okay. So if the car of S list is equivalent to the symbol we're looking for, if that's a true statement, then we're going to add 1 to count occurrences we're going to add 1 to count occurrences of S and the cooter of S list. So that's a recursive call right there, correct? Otherwise, if it doesn't match, then we're just going to boil down to count occurrences of S and the cooter of S list. If it makes you feel better for a pattern, you could have said 0 plus that. For kind of matching a pattern, this would not be necessary, but you just want to see it. If it matched, add 1. If it doesn't match, we'll add 0. Okay? That's if the car of the S list was a symbol, and if that symbol was the symbol we were looking for. All right? Now, if it's not a symbol, then what do we do? If it's not a symbol, it must be an S list by our definition, correct? And what do we do with S lists? Go ahead.
Would you call the function and then take the cooter?
Call the function and take the coder. Which function? Count occurrences? Are we adding one to it? If I'm looking at an S list as the car, then I have nothing to compare a symbol to, right? So what do? I need to call count occurrences on the car, and I need to add that to whatever count occurrences returns for the coder. Whatever the number of occurrences is for the car, which is an S list, and whatever the number of occurrences is for the coder, which is probably a list of symbols, an S list. Okay, so we're going to return plus count occurrences on the car of S list passing at S, and add to that count occurrences on the coder of S list passing at NS. Make sense? So as we go through here, until we no longer have a car, until we're out of stuff to check, we'll look at the first thing and say, if you're a symbol, I'm going to see if you're equal to the symbol I'm interested in. If you are, I'm going to add 1 to my running total, and I'm going to count the occurrences of S in the rest of the list. If you're not, I'll add 0 to my total. Not necessary, but we're just doing it for the pattern. And call count occurrences on the rest of the list. Otherwise, if you're not a symbol, you must be an S list. And what do we do with S lists? We call count occurrences on them. So the S list will pass to the first count occurrences is the S list that's at the car of our S list. And then count occurrences the second part will be to the coder of the S list. Make sense? All right, so let's look at some of our examples here that it's supposed to work for. So count occurrences, this crap should give us a 3. I have to fix, these dudes? Oh. Book spelled it wrong. Okay, there's our 3. And then we're gonna, this guy should be another 3. There's another 3. And then this guy should be W and this guy. And there's our 0. All right, that makes sense how that works? So again, the exact same structure as we had in the other ones, but instead of consing stuff, we were building up a sum using the addition operator instead of the cons, or the addition function instead of the cons function. All right, any questions on count occurrences, spelled the correct way, obviously? All right, so let's look at, so 121 was the first one? All right, so we're supposed to write, oh, these are all 2 stars. You said these were easier?
Yeah, I thought they were.
Well, good, good. Did you use map a lot?
I didn't use map once.
Really? Oh, guess I just assumed you'd use map. Maybe you don't, we'll find out.
I don't know, usually by the time I figure out I can use map,
You've already written the crap, so I got you. So we're supposed to write a function. Product takes 2 SOSs. What's an SOS? Are each lists of symbols. So why wouldn't these be called LOS?
You read the book spells things wrong.
Oh, that's star for the day. All right. So where SOS1 and SOS2 are each lists of symbols without repetition, so we're guaranteed that each list does not have symbols that are duplicated, so we wouldn't have two A's in one of them or two X's in another one, that kind of stuff. And it should return a to list that represents the Cartesian product of each of these lists. The to list may appear in any order. Okay, so what's the Cartesian product here? It's the first element here in a to list with the first element of the next one, first element here in the to list with the second element of the first one of the second one, so on and so forth. So for each of these, we're going to create a to list with each of these. Right? Okay. And this was the one that was tough? Okay, so really?
Conceptually it was easy, but the issue I kept running into is I'd go through and make the product of A and X and A of Y, but by then the second list of symbols would be empty, and I had trouble getting it to wrap back around so I could go on to B and then C.
Okay.
I wrote it in two different functions. I found that part.
Yeah, I ended up just making product a wrapper function.
Okay, so the punchline here is that we need to write a first function that goes through every element of a list. Start off with that structure. We need to go through every element of a list. And I'll call it product to start with. All right, so can I just delete all this stuff? Is that cool? So we've
So since you introduced that way of defining, can we do it that way?
to do what?
You deleted the other way of defining a function
What are you talking about?
without having lambda. You can just define.
Oh, yeah, you don't do that. Use lambdas.
But I saw it there.
Just use lambdas, it'll help.
But it's not in our official toolbox.
That's right.
Oh shit.
All right, so I also changed the names to list of symbols instead of SOS, which symbol of symbols.
Set of symbols?
Huh?
Set of symbols?
Is that what it stands for? Set of symbols? Actually, that is what it stands for. Why is it a set, not a list? No repeats. Guaranteed no repeats. So it is a set of symbols. Good thinking. All right, so what we're going to start off by doing is we're going to build our structure that goes through every element of SOS1. Okay, we'll forget about SOS2 for a second. We'll figure out what we're going to do with each of those elements later. All right, so we're going to say if null SOS1, then we're probably going to be returning the empty list because it seems like we're building a list here, right? That's our result is a new list. So we're probably going to be doing kanzi stuff. Therefore, our end game, our unwrapping of the recursion is probably going to be the empty list. So if I'm out of stuff to do, return the empty list. Otherwise, I have things I want to do. And what do I want to do? Well, I want to do something with the car of SOS1. And what do I want to do with it? I want to build a to list with that car and everything that's in SOS2. Each element in SOS2. All right. So we're going to create a second function here. Go up here. Make two lists. And this guy is going to be a lambda that takes in a element and a set of symbols if null set of symbols, return the empty list. Otherwise, what are we going to do? We're going to cons what? We're going to cons the list created with elements and car of SOS onto make two lists of element and the cooter of SOS. Make sense? So I'm going to construct a list whose first element will be a list of element and the car of SOS. So that'll create our first Cartesian product. Onto the list that's returned by make2lists, passing it the same element and the rest of SOS. So that's what make2lists will do. So down here in product, what will I do? Well, I'm going to cons make2lists onto what? The car, well, cons make2lists of the car of SOS1 onto SOS2. And I'm consing that on to what? The result of product, passing it the cooter of SOS1 and just SOS2. Like that. All right, so what does product do? It takes two lists, SOS1, SOS2, and it's only going to pay attention to emptying out SOS1. Okay, so SOS1, if we kind of come back here, SOS1 starts off as ABC, so we'll grab the A and we'll call make2lists passing the A and this guy, which will make the two list of AX and the two list of AY. Then we come back here, we call this guy getting the car, which is B, calling make2list on B along with the list XY. Make2list C along with the list XY. Cons all that together. I'll go ahead and steal this. So we have the list containing AX, AY, BX, BY, CX, CY.
No, you have the list.
We have the list containing lists, so it's extra wrapped now, right? All right. So this guy should not be a list in and of itself. This guy should not be a list in and of itself. Element. So that must be from our use of list here, right? So we're consing lists together. So what we really want to do is we want to cons Did I show you append?
No.
Perfect.
You can make it.
We could make it. Could have used our previous thing called down. It's really, well, here, let me show it to you first and then we'll write it ourselves. So I can append this, which then gets us, actually that's not right either. Hold on. I want to do a cons and I want to create a list onto these two guys. So I'm going to cons this list, which is an element, onto whatever's returned by make2lists, passing it the same element and the cooter.
That's getting you the list like.
That's getting me the
AX,
second
AY.
list.
Well, list AX and then the list AY. Within the list.
Yeah, so if I say append, I need to make a list out of this. I don't want to deviate from our structure. It's not going to be right either. It's the right answer, but all right, so we got to write append. Append is something that's built into the language, so now you've seen it. But let's go ahead and write append. So what we want append to do is we want it to take an element and another element and append them together. So it's kind of, we have two lists, for example. It creates a single list with all the contents of both of those lists. That make sense? Go ahead.
It's not a list containing two separate lists, it's just one list.
It's correct. If I append one list to another list, or one element to a, let's see, append will allow me to have, I believe append allows me to have a element and a list. So let me just do append A onto the list BC. Okay, no, it takes two lists. So append takes two lists and glues them together, producing a single list. So this is the problem we are solving. Append the list A onto the list BC, which gives us the list ABC as a flat list. Okay, so that's what we need to do. So what would happen if I cons the list A onto the list BC? What would the result of this be?
A list with the list A.
Yep, the list with the list A and the BC as this thing. So it cons the whole thing as an element on there. Okay, so how would I write append? If I want a list and a list to result in two lists stuck next to each other, you can't write append using append. Because we technically haven't been introduced to append yet. How would you write that? Go ahead.
So define append to X or whatever.
Okay.
Then we need two lists to take in.
So let's call this append 2, since it's our own version of append.
Append version 2.
Okay. This guy's going to be a lambda, and it's going to take an LST1 and an LST2. All right, what do you want to do with it?
You need to check to see if the first list is null and then you print out the second list. Or not.
Return.
Okay, so if LST1, if null, LST1, then what do we return? We return LST2. Okay, otherwise, what if it's not?
We do the appending.
Okay, how do we do the appending?
Take the car
list one.
Car of list 1, and pass it on to what? Append 2 of the cooter list 1 along with list 2. All right, so there's append 2. Same pattern as we just had. This is just a mini version of it where we have two lists. We burn through our first list, consing each element onto something. And then in the end, rather than returning the empty list, we return that second list that we're putting everything onto the front of. All right, so this is append. The good news is the function append already exists in the language. So now you have access to it, but you could have written it yourself.
It's in our toolbox now.
In your toolbox now. All right, so that's product. 1.22, filter in. Okay, so this gets down. I had a second quiz question in mind. I'll go ahead and ask it out loud for Pebbles. So, what does it mean?
He doesn't know what it means.
What does it mean when I say that functions in Scheme are first-class objects or first-class variables? What does that mean? You would have rather had that one? You just said this is an actually easier question than I asked you before. Do you know the answer to this one? What does it mean when I say in Scheme functions are first-class variables or first-class objects? You could also say, what does it mean to say procedures are first-class variables or first-class objects? Or lambda calculus expressions are first-class variables or first-class objects. What does that mean? All right, I'll open this up to the audience now, since Pebbles isn't helping. Go ahead.
Does that mean they're undefined?
No, I mean that's what a definition of a lambda calculus expression is. It's an well, not undefined. It would be an unnamed function. Call on or use themselves. It's possible you know what you're talking about, but tell me. I'm not convinced at this point.
Like a function can call on itself within itself.
That's recursion.
But I mean,
Function can be a parameter of a function, like
Functions being first-class objects means that we can pass functions as parameters into other functions. Okay, not just itself, but any function. We can pass functions in as parameters. All right? So that's what it means by saying that. So now we have something called filter in. And pred is a predicate. What's a predicate? It's a predicate, Pebbles.
True or false? True or false?
Function that boils down to true or false. Very good. 1 for 3. You're learning. You should probably, instead of learning 2 classes ago, you should learn 3 classes ago. 3 classes ago was predicates? 2 classes ago? Okay, you might want to catch up a bit. All right. So filter in takes a predicate and a list, or returns the list of those elements in LST that satisfies the predicate pred. That is where all of them are true. So it returns a list of only the elements in LST that satisfy the predicate pred. Okay? Should be our normal structure, right? What's the name of this? Filter in? That's what it's called?
Yeah.
Filter in, and this guy takes a predicate and a list, except it's got to be. If null LST, then we're going to return the empty list. Else, if pred, when applied to the car of LST, if that's true, then we'll cons the car of LST onto filter in, passing it the predicate and the cooter of LST. Otherwise, we'll just return filter in of the rest of the list.
Won't work.
Okay, why not?
Because you didn't define it.
How about that?
No.
I'm getting an error message. It's expected a question to answer only 2 parts.
On this code? Oh, here, let's test it. Let's 2.7. Let's 2.7. Any foo? So you probably need to write yours better.
It's the same thing.
I guarantee it's not. It's probably highly, highly similar. Very similar. Yeah, in scheme we get diarrhea of parentheses. Parenthesis diarrhea. All right, so again, this follows our structure while you're looking for your error here. So again, you must make sure you define your variable, blah, 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 whatever. All right, so this guy takes in a predicate, which is a function that takes a single parameter and returns a true or false, as well as a list. Now, one thing we could have done here is we could have mapped that predicate onto the list, gone through and found all the places where it was true, and then shown the equivalent places inside of our other one, but that would have actually made this significantly more complex. In any case, we just went through until LST was out of stuff. So we kept whittling down LST because each time we went through, we applied our predicate. That's a word I want you to kind of remember when I say applied the predicate. So that's something that's going to come up a lot when we start writing our own language. Okay, so we apply a function to a set of parameters. So we're going to apply our predicate to the first element of that list, getting a result. If that result is true, that's what that essentially says. If the result of that predicate boils down to true, then we're going to cons that element, the car of that list, onto our running total. Not the result of the predicate on the car, but the car itself. Because that's what we're supposed to do here. We're supposed to create a list of all the elements of LST that get a true when the predicate is applied to it. Okay? So if the predicate boils down to true when applied to the car of the list, we're going to cons it onto our answer. What are we consing it onto? Filter in of the same predicate onto the rest of the list. If it's not true, then we're just going to go ahead and call filter in predicate on the rest of the list and not cons the car of the list on because it didn't fulfill, well, the predicate didn't boil down to true. Go ahead.
So is predicate like a like when you put in that that element, I guess, you're checking in this to see if it matches something in the function, and if it's true, then you move on to the next part, I guess?
Well, not if it's true you move on to the next part. We're always moving on to the next part. We're only consing it onto our answer if it was true. But our predicates here are number and symbol. Okay, so if I change this though, remember a predicate is just a function that takes one parameter, returns true or false. So I can pass a lambda that takes a single parameter, and this guy maybe returns equals XA. So this guy should only boil down to the list containing an A, because that's the only element in the input that fulfilled that. If I throw another A in here though, now I get a list containing A and A. Did I answer your question? I felt like maybe your question was poorly asked.
Yeah, because I don't really get predicates, I guess.
All right, well, so this is a predicate.
Okay.
So a predicate is a function that takes exactly one parameter. 100% of the time, predicates take one parameter, and they result in a true or false answer. So here's a stupid little predicate that only returns true when the parameter you passed it is equal to A. That's it. False otherwise. It only returns true when you pass it an A. The predicate that we had in here before was the predicate that's built into the language called number. This guy returns true when whatever you pass it is actually a number. False otherwise. The other one was symbol. That's a predicate that takes, again, one parameter, very important part of predicates. They take one input, one parameter. So the symbol one takes in one parameter, returns true if that parameter is a symbol. False otherwise. Well, makes sense what a predicate is? Kind of. It's kind of important. So tell me where you're still kind of hung up. Or try to tell me where you're still kind of hung up, so I can get to the bottom of where your confusion is.
I guess I'm just not really sure about the structure of how a predicate works. I mean, I get just with how you build a predicate up and how it results in the answer. I don't know.
Okay, so sounds like maybe you have a confusion doesn't have anything to do with predicates. All right, so let's go this route. First of all, a predicate isn't like all it is a special name that we've given to a function that meets a certain criteria. Okay, so any function that takes one parameter and returns true or false, we're calling a predicate. We could easily call it a cat or a dog. Okay, we've just decided that those types of animals are predicates. So functions that take one parameter and return true or false are predicates. If it takes one parameter and returns a number, not a predicate. Okay, if it takes two parameters and returns a true or false, not a predicate. Must take one parameter and must return a single value of true or false, then it's a predicate. Okay, so that's what a predicate is. It's a function. Now we get back to the other side of it, which was how are functions treated as first-class objects in Scheme. That means we can pass a function. So that number 2 there is a function. That's what that guy is. So if I just say number 2, if I just say number question mark, that just gives us the spit back. Let me do this. Define blah to be a lambda, takes in an x, and returns true only if x is equal to a. Oh, it always just spits it back. It doesn't tell me bone structure. Yeah, so this is a predicate. Blah is a variable which holds a predicate. Okay? But now what we can do is we can actually call filter in, passing it blah, which is a variable which happens to contain a predicate. So now I'm passing a function into filter in, along with this list. Let me just steal this list. Okay, so filter in takes two parameters, a predicate and a list. The predicate in this case, blah, is a variable which boils down to this expression, this lambda calculus expression, which meets the criteria of a predicate. Okay, and it's important that it's a predicate in this case because we are going to pass each element of this list. That's one element, that's another element. It's not a list of elements, that's an element in and of itself. That's a two list. Another element, and another element. We're going to pass each of those guys in turn into this lambda expression as x. And it's only going to return true when that element is actually an a. So that's why in the end we only get a and a, because those are the only two guys for which that predicate returned true. Makes some more sense? Yeah. All right. Okay, that was 122. Any other questions on 122? 123, list index, predicate LST, returns the zero-based position of the first element of LST that satisfies the predicate pred. If no element of LST satisfies the predicate, then list index should return false. All right, so this gives us a little bit of a new structure here. What's it called? List index. To be a lambda that takes in a pred and a list. And we're supposed to return the number, the zero-based index of wherever in list pred first returns true. Okay? Then, if we get through the entire list and it never returns true, we should boil down to # f, which is false. That's the hard-coded value for false. All right, so same structure as we've had all along. So if null LST, then we're going to boil down to if we've hit this point, we've run out of crap, we haven't boiled down to an answer yet, our answer is going to be false. Right? Okay. Otherwise, we're going to ask the question, if pred, when applied to the car of LST, If that guy is true, then we're going to boil down to the car of LST. If it's false, then what are we going to do? Actually, we're not going to boil down to the car of LST. We're going to boil down to we need a number.
0.
We're going to return 0. Otherwise, we're going to return plus 1 onto list index, passing it pred, and passing it the cooter of LST. All right, so this kind of mixes a couple of our structures together. This is kind of like counter-occurrences, where we're building up a sum. When we finally find something that matches it, we're going to return a 0, so we don't add anything additional to our sum. We kind of stop the summing by throwing a 0 in there. So this will finally end with a number. But if we end up running out of things in our list and never actually find something where pred boils down to true, then we'll just boil down to false. So this guy returns 2 different types of things. Either returns false or returns a number. Go ahead.
It's going to throw a fit if you return false and then try to add 1 to that. Because you can't add 1 to false. So if it returns false and then you go backwards in the recursion.
Yeah, I get it. So when this boils down to false, this would boil down to false,
Right.
which would then try to add 1 to that guy, right? So what we can do is
You can just
Ask
check
another
if the
question.
recursion calls a number and then you add it. Otherwise, you just return out.
yeah.
I don't know if there's a better way to.
You gotta throw an if in there. Ugh. I don't like this either. It's kind of a crappy. It does show a need for something else, but so we'd call list index, passing it the predicate, and passing it the cooter of LST. But we're interested in whether or not that guy is a number. If that guy is a number, then we're going to return 1 plus this guy. So we're actually calling the function twice. Else, yeah, we don't have to call it again. We're going to say false. So this actually, so really what's happening here is we're calling this function once to test its result, and then again to actually use it in the event that its result was a number. All right, so this is pretty inefficient. Where this would be helpful, what this shows, well, let me ask you this. What does this show us a need for? What kind of language construct would be helpful for us here? Inline if statement would still, I mean, basically if statements in scheme are inline, right? So it would still require us to call it twice. Won't this guy and this guy boil down to the exact same value? So what do we do when we need the same value more than once? Throw it in a variable. Problem is we don't have the ability to grab to store variables here. Now we have kind of a roundabout way of dealing with variables. I haven't shown you yet, but it's something called set bang. So I can say define A to be 5, and then I can print out A, and then I can do set bang A to be, I guess I'm doing symbols 6 and 5, and then I can print out A and I get a 6. Okay, so set bang allows me to change the value of an existing variable. So I could define kind of a temporary variable up here and use it over and over and over again here. So before this, I can do something like define temp to be -1, let's say. And then in here, I can say, let's see, that's number. Oh, that's going to suck too. Yeah, you don't want to do it this way. But your answer's still right about the, we need to be able to store local variables. And there's something we're going to be looking at either today or next class, but something called lets. And what a let lets us do is it lets us get the value of a variable. So it lets us create a small scope, our own little variable environment. So I would do something here like inside here I would say let x be the result of this guy. Then, if x is a number, add x to our running total, otherwise return false. So now we have this little special environment here in this, with this let. That inside this environment we have a local variable named x, and x is equal to the result of calling list index on the rest of this whole thing. That make sense? So let me steal a list index example. Oh, I need to run this here first. Oh, sorry. Actually, hold on. No, it should be that. I think it's this. There we go. I'll show you the syntax of that here in a second, just so it's a little bit clearer. So there's our 1. So in this particular case, we only actually made the recursive call once instead of twice. So a little bit better. Let me show you the generic syntax for a let. So we can add it to our toolbox just in case you need it for your homework. All right, so we added append, and we added let to our toolbox. So a let, this guy, creates a local environment allowing us to define variables to use during the run of a procedure or function, however you want to think about it. Okay, syntax for a let is open parenthesis, the function name is let, and let takes in a list of toLists. Okay, so, and each toList is var name, var value. So that would give us one variable in that case. If you want two variables, you can have var name, var value. Okay, so it's a list of toLists, like a dictionary is what the parameter to let is. That's the first parameter, is a list of toLists. The second parameter is the body of that environment, which in our case here we have like the whole if conditional dealie. Okay, so that's the generic syntax for a let. So anything that happens inside the body is governed by the local variable scope created by this dictionary. So showing you this in the code, here is our dictionary. That's our dictionary. That's our dictionary. That's our dictionary. Right? Our dictionary is a list containing one to list. That's our one to list. That one to list is a variable name and its corresponding value, which is the result of calling list index, passing it the predicate, whatever. So this is the value assigned to this variable name x. Okay, that's that single to list. That's our dictionary, which in this case is a list containing exactly one to list, one variable value pair. But we can have more if we'd like. So I can put a second variable value pair right here. I can say y is 2, for example. Now I have two variables, an x and a y. And this would still run because I didn't even use the y. If I had access to it, it's there for my own enjoyment. Here we could actually say y is the list containing -1, let's say. So instead of returning false, we can return y if we'd like. And then what we can do here is, let's see, now we have a list. Here, let me just take this list out. No more list. We'll pass the predicate list in here. Now we should get the list -1. There's my list -1. Because none of these guys fulfilled the predicate list. So it returned the value of y in that case. Make sense what a let does? Gives us a local variable environment so we can store stuff during the run of our procedures. Comes in handy. There's actually a couple of different forms to lets. I think 2 classes ago when we were talking about the equal sign versus EQ question mark versus EQV question mark versus equal. Each one kind of works at various levels of bone structure, and we'll get into that. There's a similar type of thing here with lets. We have a thing called let, we have a let star, and then we have something called a let rec. We'll talk about those in passing, but really it comes down to what are the capabilities of that variable environment. The let variable environment is the simplest form of it. We're going to actually be inventing our own variable environments before very long. We're still kind of learning the scheme stuff, but I'll introduce those things later when we implement our own version of let and how that works and what its weaknesses are. Why can't it do something else that we might want it to do? All right, so quick punchline. I'll just give you the foreshadowing version of this. A let does not allow us to define variables in terms of other variables in the let. So for example, I cannot set y equal to plus x1. Okay? I can't do that with a let. Because in a let, each of these guys are evaluated individually, so this guy does not know about x, because we defined x right here. Make sense? A let star would allow that. So if I do let like this, it's going to scream at me, x, this variable is not defined. If I do let star, it's going to say, oh, okay, everybody's cool. Except now it's I gave it a list because this guy boils down to a list. Because I made it a list, but whatever. And then we have let rec. And let rec allows us to actually do recursion inside of it. So we can have variables inside of the let which are equal to lambda expressions. So they're equal to unnamed functions. And then we can recursively call those functions inside of the let environment. So let recs support that. Things you don't have to worry about right now, just kind of foreshadowing. That's the advancement of our local variable environments. For right now, we can create a couple of variables that aren't related to each other directly. Everything's cool. Okay? So that was, we tested this, right? Before I did all these variables and stuff, this worked? Okay. That's that. I'm lost. Okay, here we go. 124. Every returns false if any element in list fails to satisfy pred and returns true otherwise. So if any element in list fails to satisfy pred and returns true otherwise. Ooh. This is a very, very, very good function for map. Let's write it I'm going to call it the bad way first, and then we'll, oh, this is a good one. This is a good one. Okay, so we're supposed to define every. Did anybody write this one with map? Did anybody write? Okay. So exciting. All right. Let's make sure I didn't crash something here. Oh, that's right. I'll just make it a let star so it doesn't scream anymore. Everybody's happy. Good. All right. So I'm defining every. Was it a question mark? Every. What does the naming convention question mark typically indicate? It's a predicate. Yeah, it's not a rule, just happens to be a scheme naming convention that whenever you have something with a question mark at the end of it, it tends to be a predicate. Number question marks predicate, list question marks predicate, symbol question marks predicate, those types of things. So that happens to be a naming convention. Just like in Java, class names typically start with a capital letter. They don't have to, but they typically do. All right, so every pred and LST. So this guy's going to be a lambda that takes in a pred and an LST, and it's supposed to return true if everything in the list has a if even one element of that list boils down to false. When pred is applied to it, we should return what, false? So every should return true if every single element in LST returns true when pred is applied to it, and false otherwise. So we're going to use our normal structure. So we're going to say if null LST, then we can go ahead and just return true. Still kicking, right? We'll finish kicking, I guess. Else, if not pred car LST. So if when we apply pred to the car of LST, if that's not true, then we'll boil down the false. Otherwise, we're going to call every passing it pred and the cdr of LST. Like that. So there's our false, because not all of these guys are numbers. And then we should have a true version where every one of them is a number. Make sense? All right. Anybody see how we could have used map for this? So let's define every two question mark. First thing I'm going to do is I'm going to map, lambda pred LST. First thing I'm going to do is I'm going to map pred onto LST, producing me a list of a bunch of trues and falses, right? And I'm going to map and onto that. Okay, do the same thing. And true and false, and a bunch of trues. I'll switch both of these to every two. Four.
Oh, parentheses.
Oh, thank you.
Parentheses diarrhea.
Yeah, parentheses diarrhea. So map, wait, hold on, no. It's not, it shouldn't be parentheses. So map the function and onto the list returned by map of this. Can't map and onto that. So not treat and as a function? Is it not and like that? Is it and like...
Isn't there and map the function?
Who?
Isn't the function and map?
I don't think so. Map takes a function and a list to map onto. Is it this guy? Let me try something here real quick.
Well, apparently, wrap the document the right way and say there's a function called and map that does what you want.
I don't want to use that. I want to use the normal map. But why won't it let me pass and to it as a normal map? Because I can apply and. So for example, let me show you this here. All right, so here's the result of this. So if I take this list and I say and that, I found only one. Okay, so I want to I want to map. I want to map and onto that list. Oh, it really parses that funny, doesn't it?
Well, is the and, do you put parentheses before the and?
Who?
Parentheses before that.
Well, that would be how you use and, but I'm taking the function and applying it to all these elements. I think the real problem is and takes what's called a stream of inputs. I can pass as many things to the and function as I want, when this has to be something that takes in a single function, it takes in a function that has a single parameter. So what I could have, I would have to write my own lambda. So while this would be a cool map thing, it would actually not been a convenient given how easy this was otherwise. It's a good thought. There's actually a way I could have mapped it across, but not something we would have to write another function. All right, and lastly, exists. Returns true if any element of list satisfies pred and returns false otherwise. Okay, so we're only looking for trues. So this is exists. So let's go ahead and grab every. We'll call this guy exists. So if the list is null, if I've run out of stuff and didn't hit one of them that return true, I'll return false. Otherwise, if I find a true for the car of the list, then I'll return true. Otherwise, I'll call exists on the predicate and the cooter of the list. So pretty similar to what every was, except that's exists. Oh, very nice. Guess we're not testing this one. Definitely not testing this one. Testing this one. Nailed it. All right, I think it works. Looks like it works.
You could just change every two to exists.
No. All right, so this one, we have at least one on there, so that should be true, and we have a whole bunch of them, so they both should be true. True. All right, questions? Is that all the assignment was due today? All right, so for next class, 1.26 through 1.30. All right, so things will start getting pretty interesting with those. 1.26 through 1.30. I will see everybody on Tuesday.